The soul of a great wine was written millions of years before the first vine was planted.
It's a stunning realization when you actually trace it back.
Yeah.
Because you aren't just tasting agricultural output. You are tasting a geological epoch.
Exactly. And we are stripping away the poetry today.
Yeah.
Because if you are someone who loves wine, you constantly hear these buzzwords.
Right. Like minerality.
Right. Minerality or terroir or, expression of place. And it sounds incredibly romantic.
It really does.
But our mission for this deep dive is to look purely at the empirical science. We've got this massive stack of sources on the table today: geological databases, viticultural research papers, technical soil guides.
Heavy reading.
Oh, yeah. Because we are going to trace the unbroken chain of cause and effect, starting with the shifting of tectonic plates and the crushed fossils of prehistoric cephalopods.
All the way to the microscopic biological engines inside a vine root.
Right. The stuff that determines the exact acidity and structure of the liquid in your glass.
And we have to start that trace with a massive geological structure that dictates, well, almost everything we think of when we think of classic old world European wine.
Okay, lay it on us. Where do we begin?
If we want to understand regions like Burgundy or Chablis, Champagne, Sancerre, we have to look at the Paris Basin.
Right, so if you look at a modern topographical map, the Paris Basin appears as this immense, broad structural depression across northern France.
Yeah, spanning roughly 110,000 square kilometers.
It's huge.
Yeah.
But it isn't just a shallow valley. Geologically, the sources call it an intracratonic sedimentary basin.
Let's define that, because it sets the physical rules for everything that follows.
Please do.
So a craton is the old, stable, rigid core of a tectonic plate.
Okay.
An intracratonic basin forms when a section of that stable interior crust slowly subsides. It basically sinks downwards over millions of years, creating a massive bowl-like depression.
So it's a giant sinking bowl.
Exactly. And over time, that sinking bowl acts as a catch basin for whatever environment exists above it.
And about 150 million years ago, during the Jurassic period, the environment above it was water, right?
Yeah. Much of Western Europe was completely submerged.
But not like a freezing ocean.
No. It wasn't the deep, dark, freezing ocean we might picture. It was a warm, shallow, carbonate-rich epicontinental sea.
Basically a tropical marine environment stretching across what is now France.
Right. And that sea is the engine of our entire story. Because a sea is fundamentally a biological factory.
Right, with all the microscopic life.
Exactly. You had microscopic marine algae, specifically coccolithophores.
Coccolithophores?
Yeah, they're single-celled phytoplankton that construct tiny hubcap-shaped protective plates out of calcium carbonate. Those plates are called coccoliths.
Okay, so phytoplankton. What else?
You also had sea urchins, early ammonites, squids, and just vast reefs of bivalves and oysters.
And naturally, as these organisms live out their life cycles, they inevitably die.
Yeah, and they drift down to the seafloor. It's this continuous microscopic rain of biological debris.
Just raining dead shells for millions of years.
Right. It is an unimaginably slow accumulation. I mean, we're talking about deep time here.
Yeah, the scale is wild.
It takes broadly 1 million years to lay down just 10 meters of this sedimentary debris on the seafloor.
Wow. 1 million years for 10 meters.
Yeah. But this epicontinental sea remained in place in various forms for tens of millions of years.
So that really adds up.
Exactly. As the layers build up, the sheer hydrostatic pressure of the ocean water above, combined with the immense weight of the accumulating debris itself, it initiates a process called diagenesis.
Right, diagenesis, which is the physical and chemical changes that turn loose sediment into solid rock.
Correct. The water is literally squeezed out of the pore spaces. The calcium carbonate recrystallizes and acts as a cement.
Cementing all those tiny shells together?
Yes. And that loose biological debris compacts into massive, solid beds of limestone, chalk, and clay-rich marl.
And in the depicenter, which is the deepest, most central part of the Paris Basin, these sedimentary sequences stacked up to an astonishing 3,000 meters thick.
3 kilometers of solid, fossilized sea life.
That is just mind-blowing.
It is. But the crucial part of this history is that the sea wasn't static. It wasn't one uniform environment for those tens of millions of years.
Right, because the climate shifted, tectonic microplates adjusted, and global sea levels rose and fell.
Exactly. And because of those changes, the Paris Basin became a staggering geological timeline.
Like a snapshot of different eras.
Yeah. Sometimes the sea was relatively deep and agitated, swept by really strong currents. That environment laid down very hard crystalline limestones.
Okay.
But later, the sea level might drop, creating calm, muddy, wave-protected coastal lagoons. And that environment laid down softer, clay-heavy marls.
So different water, different rock.
Precisely. And during periods when the surrounding terrestrial land masses were eroding, rivers would wash fine silts and clays into the basin, creating entirely different stratigraphy.
Okay, let's unpack this for the listener. So the Paris Basin is basically a giant geological soup bowl that slowly dried out.
That's a good way to look at it.
And as it dried, it left behind distinct rings of hardened ingredients, limestone, clay, and chalk along its edges. If we could slice a core sample straight down through the center, we'd be looking at a layer cake of distinct epochs.
Yeah, the Jurassic, the Cretaceous, the Tertiary.
And each layer chemically encodes the exact marine environment of that specific million-year interval.
And because it's a basin, a sagging bowl, those sedimentary layers don't just sit flat.
Right.
As the center of the bowl sinks deepest, the edges of those sedimentary layers slope upward along the margins of the basin.
Okay, so the edges are tilted up.
Yeah. And when the sea eventually retreated permanently and terrestrial erosion went to work, those upward-sloping edges were exposed to the surface.
Leaving behind distinct concentric rings of differing rock ages outcropping across northern France.
Exactly.
But wait, if the basin is fundamentally a gentle sloping structure, that presents a geographical puzzle.
How so?
Well, when you stand in the middle of a premier vineyard in Burgundy, you aren't standing on a gentle, continuous slope.
Oh, far from it. You're looking at a jagged, highly complex, steeply pitched escarpment, where the soil seems to change completely every few rows. So how do we get from a flat seabed to the dizzying complexity of the Côte d'Or?
To get the hillsides of Burgundy, you have to introduce immense geological violence.
Geological violence. I like the sound of that.
The flat, peaceful, sedimentary layers of the Jurassic Sea had to be shattered. And that brings us to the Alpine orogeny.
Which is the building of the Alps.
Yes. Starting roughly 65 million years ago and peaking around 2.5 million years ago, the African tectonic plate drove northward.
And smashed into Europe.
Right, colliding with the Eurasian plate. This was a monumental crustal collision that closed the ancient Tethys Ocean and forced the Earth's crust miles into the sky to create the Alps.
It's hard to even picture that kind of force.
And the kinetic energy of that collision didn't stop at the mountain peaks. Massive, compressive shock waves rippled far to the north and west, tearing right through the solid limestone bedrock of the Paris Basin. You can picture the sheer force required to take a limestone sheet 3 kilometers thick and just forcefully buckle it.
It cracked, folded, and inverted those horizontal sedimentary layers.
Wow.
And then, as the tectonic pressures eventually shifted from compression to extension, meaning the Earth's crust in that area began to pull apart slightly, a massive structural failure occurred.
The bottom dropped out.
Exactly. Roughly 23 million years ago, a huge block of the crust simply collapsed downward between two parallel fault lines. Geologists call this the Bressegraben.
So when that central block dropped, it just left the edges standing high in the air.
It left a 500-meter vertical escarpment exposed on the eastern edge of the massive central.
Half a kilometer straight up.
A sheer, fractured cliff face of ancient marine rock suddenly looking out over a deep valley. And that escarpment is the Côte d'Or.
The golden slope of Burgundy. That's incredible. So the fault line literally sliced the geological layer cake open.
It did.
Taking rocks that were deeply buried and exposing them to the open air.
But, you know, the tectonic violence of the alpine shockwaves ensured it wasn't a clean vertical slice. The bedrock was folded entirely out of order.
Right, it's chaotic.
Highly chaotic. This is why you find structural anomalies like the Volnay syncline.
A syncline is a downward U-shaped fold in the bedrock, right?
Yeah. In Volnay, the tectonic pressure forced the older, deeper Jurassic layers to plunge deep underground, leaving only the younger, top layers exposed on the slope.
Okay, and the inverse of that is an anticline.
Exactly. An A-shaped fold where the deeper rock is squeezed and pushed upward.
Like the Givry anticline.
The Givry anticline is a perfect example. In Givry-Chambertin, those very same deep, ancient bedrocks that sank in Volnay were aggressively forced back up to the surface.
Which explains so much about Burgundy wine.
It really does. This is why you can have two vineyards just a few miles apart, sitting on rocks that were formed millions of years apart in completely different oceanic conditions.
Okay, let's get highly specific about what those oceanic conditions actually were, because this is where the empirical science of terroir really locks in.
Let's do it.
In the Côte d'Or, you map these complex fault lines, and you find two very distinct rock formations right next to each other. The first is crinoidal limestone.
Crinoidal limestone was laid down roughly 170 million years ago during the Bajocian stage of the Middle Jurassic.
170 million years ago.
Okay. And the depositional environment, meaning the physical state of the ocean at that time, was high energy.
High energy meaning waves.
Yeah. It was a relatively deep tropical sea, aggressively swept by strong wave action and ocean currents. It was a turbulent environment.
And the dominant biological life forms contributing to the sediment were crinoids, commonly known as sea lilies.
Right. But despite the name, they aren't plants. They are marine echinoderms.
Animals.
Yes. They have long, calcified, articulated stems that attach to the seafloor, with feathery arms to filter nutrients from the rushing water.
So how did they become the rock?
When they died, that violent wave action shattered their calcified stems into millions of tiny crystalline disks. These disks compressed over time to form an incredibly hard, dense, crystalline limestone matrix.
So the rock itself is a monument to a turbulent, high-energy environment.
Exactly.
Now let's look at the viticultural result. When a winemaker plants Pinot Noir directly into the shallow topsoil over this fractured crinoidal limestone, what actually happens?
The physical properties of the rock dictate the vine's metabolism.
Ah, so.
Because this limestone is so dense and crystalline, it is highly porous but holds very little surface water. The water drains away rapidly through deep microfissures.
So the vine is immediately thirsty.
Yes, the vine's roots are forced to fight their way through these hard fissures. This physical struggle restricts the vine's vegetative vigor.
Meaning it stops growing leaves.
Right, the energy shifts away from growing leaves and shoots and concentrates into the fruit.
So what does that taste like?
The resulting Pinot Noir is typically described as possessing intense verticality. The wines are vibrant, fiercely structured, with a highly focused mineral tension and brilliant aging potential.
A strict architectural wine born from a hard, turbulent rock. That makes perfect sense. Now, let's contrast that with the second major formation, which sits just across the tectonic fault lines, Austria Cuminata Marl.
Okay, so this formation dates to the early Bethonian stage, roughly 168 million years ago.
So just 2 million years after the crinoidal limestone.
Right, but just 2 million years later, the environment had completely transformed. The sea level shifted, the violent currents were blocked, and the area became a calm, shallow, muddy coastal lagoon.
A totally low-energy environment.
Very calm. And a different environment means different biology. The sea lilies were gone.
But replace them.
This calm, muddy lagoon was densely populated by a specific species of tiny, flat oyster called Austria acuminata.
Oysters?
Yeah. Millions of generations of these small oysters lived and died in the mud. Over time, this compressed into marl.
And marl is essentially a sedimentary rock that's a roughly equal mixture of clay and calcium carbonate, right?
Exactly. It's a dense, sticky, gray-blue rock, absolutely studded with intact fossilized oyster shells.
And when you plant Pinot Noir into this clay-heavy Austria acuminata marl, the vine behaves entirely differently.
Completely differently, because clay alters the hydrology.
Okay, let's get into the hydrology.
Clay particles are microscopic and flat, with a massive surface area that inherently holds onto water molecules and dissolve nutrients.
So it's like a sponge.
Yes. The roots in the marl don't face the intense, rapid drainage of the hard limestone. They sit in a cooler, more consistently hydrated matrix.
Meaning the vine experiences less acute hydric stress.
Consequently, the grapes produce a different profile of secondary metabolites. Pinot Noir, grown in this marl, yields wines that are texturally broader, more flesh-driven on the mid-palate.
With an earthy weight and a darker, more brooding fruit profile.
You've got it.
Now, I have to step in here and challenge this premise, because here is where it gets really interesting, and frankly, where a lot of wine writing drifts from science back into romance.
Oh, I know where you're going with this.
Right. We have two distinct rock types. Wave-swept sea lily limestone and muddy oyster marl. And you're saying the wine from the limestone is tense and structured, while the wine from the marl is broad and earthy.
Yes.
The romantic interpretation is that the vine is somehow tasting the oyster or absorbing the energy of the ancient sea. But mechanically, plants do not eat rocks.
They certainly don't.
A vine root absorbs water, nitrogens, potassium, iron. It sees chemical ions. It does not know what an oyster is. So what is the actual empirical mechanism transferring this geological history into the glass?
That is the essential question of terroir. You are absolutely right. The vine is not absorbing the flavor of a fossilized oyster.
Thank you.
The mechanism is entirely hydrologic and thermal, dictated by the physical architecture of the specific rock.
Okay, walk us through the mechanics.
It works like this. The chemical composition of the grape at harvest, its ratio of sugars, acids, tannins, and aromatic compounds is a direct stress response.
Stress response.
Right. A vine that has unlimited water and nitrogen will produce a massive canopy of leaves and dilute, uninteresting grapes.
Because it doesn't need to reproduce urgently.
Exactly. But a vine that is subjected to specific, highly timed periods of mild hydric stress will radically alter its internal chemistry.
It panics a little.
It shuts down vegetative growth and pumps complex secondary metabolites, anthocyanins, flavanols, tannins, into the skins of the grapes to protect the seeds and ensure reproductive success.
So the rock acts as a hydrologic regulator.
Precisely. The crinoidal limestone fractures in a way that drains water instantly, but holds deep humidity in its capillary network, creating a highly specific, continuous low-level stress.
And the marl.
The Austria acuminata marl holds water much closer to the surface due to the clay, delaying that stress until much later in the ripening season. And it keeps the root zone physically cooler, which delays the breakdown of malic acid in the grapes.
So the fossils.
The fossils are merely the diagnostic markers that tell geologists which specific physical matrix they are looking at.
I love that. The oyster isn't the flavor. The mud the oyster died in is the physical sponge that controls the water.
That is the exact empirical reality.
That makes complete sense. Geology dictates hydrology, hydrology dictates plant stress, and plant stress dictates the chemical compounds in the final wine.
It's an unbroken chain.
And what makes Burgundy so singular is that because of those alpine tectonic shock waves, these vastly different hydrologic environments aren't miles apart.
No, they are smashed right up against one another.
Right. If you look at the mapping work done by geologists in the Côte d'Or, you can see massive fault lines slicing straight through individual vineyards.
Take the Grand Cru of Bonne-Mère.
Okay.
The western boundary of the vineyard sits squarely on the white Austria acuminata marl. The eastern section of that exact same vineyard drops across a fault line onto the red, iron-tinged crinoidal limestone.
Meaning a vigneron can literally step 3 paces to the left, cross an invisible underground tectonic fault, and completely change the hydrologic environment they are farming.
And that is why a wine from one side of a tiny dirt road in Burgundy can taste fundamentally different from a wine on the other side.
That is just phenomenal. Now, if Burgundy is defined by this vertical chaos, these shattered, folded fault lines, what happens when we travel slightly northwest out of the Côte d'Or?
Terroir.
To regions defined by deep, horizontal geological consistency, where the rocks are mostly flat.
Then we find regions where the specific nature of a single horizontal sedimentary layer is so dominant it entirely dictates the global identity of the wine. We move into the Kimmeridgian stage.
The Kimmeridgian, which forms the bedrock of both Chablis and Sancerre.
Yes, the Kimmeridgian is arguably the most famous geological footprint in viticulture.
Let's define it for everyone.
The Kimmeridgian is a stage of the late Jurassic, dating from approximately 157 to 152 million years ago.
And the name.
The name originates from the village of Kimmeridge on the Dorset coast of southern England, where 19th century geologists first identified this Pacific sedimentary sequence.
Because, as we established, the Paris Basin is massive. Its northern edges extend all the way under the English Channel.
Exactly.
So what are the physical and chemical properties that make Kimmeridgian rock so highly prized?
Physically, it is a sequential layering of hard, compact limestone beds, alternating with softer, highly clay-rich, gray-blue marl.
Like a literal layer cake.
Yes. Chemically, it is defined by a massive concentration of active calcium carbonate, usually ranging between 25 and 35% of the soil matrix.
That's a lot of calcium.
But visually, its diagnostic signature is another fossil. Not a sea lily, not the Bethonian oyster, but a completely different species of tiny oyster called Exagera virgula.
Exagera virgula. They are distinctively comma-shaped, right? Or slightly curved like a crescent moon, usually just a few centimeters long.
Yes, and they are incredibly abundant. In 1904, a viticultural professor named Georges Chapaz conducted extensive subsoil surveys of Chablis.
What did he find?
He found that the marl layers were utterly packed with these tiny fossils. In some outcroppings, the rock appears to be entirely constructed from compressed Exagera virgula shells.
Just billions of little commas. So why is the specific matrix, the alternating hard limestone and the oyster-packed clay marl, the ultimate environment for growing Chardonnay and Chablis.
It creates an optimal, self-regulating hydraulic system that perfectly balances the cool, marginal climate of northern France.
How does it self-regulate?
The clay-rich marl layers act as a subterranean reservoir. During the dry summer months, they hold just enough moisture to keep the vine functioning.
But not too much.
Right. However, the intercalated beds of hard limestone ensure that gravity pulls excess water away rapidly during heavy spring rains. The roots are never asphyxiated by standing water.
So it prevents rot and excessive vegetative growth. But how does it affect the chemistry of the Chardonnay grape?
The extreme level of calcium carbonate in the Kimmeridgian soil strongly influences the vine's uptake of potassium and other contagions.
Okay, mineral interaction.
This specific mineral balance, combined with the low temperatures of the region, inhibits the vine from rapidly metabolizing the malic and tartaric acids inside the grapes.
So it locks the acid in?
The acidity remains trapped at incredibly high levels. This is the physiological mechanism behind Chablis' signature profile.
Which is that fiercely dry, steely, structurally tense wine.
With a piercing acidity and a distinctively saline, almost iodine-like finish.
Now, to really grasp the impact of the Kimmeridgian, it helps to see what happens when it's removed from the equation, because not all of Chablis sits on this oyster-packed marl.
That's true. As you move up the slopes and onto the higher plateaus surrounding the main valleys of Chablis, you step out of the Kimmeridgian into a younger geological layer.
Called the Portlandian stage.
Yes, formed roughly 135 million years ago.
So the sea level had changed again.
It was much higher, and the surrounding land masses were contributing far less clay runoff into the basin.
Changing the recipe of the sediment.
Consequently, Portlandian limestone is noticeably harder, more compact, and crucially, it has a much lower clay fraction. And it almost completely lacks the Exogyra virgula fossils.
It's a drier, harder rock, and the French appellation system literally legally recognizes this geological boundary.
They do. The entire hierarchy of Chablis is mapped onto the bedrock.
Really? All of it?
All 7 of the Grand Cru vineyards, Le Clos, Vaudésir, Valmore, and the rest, are clustered on a single, continuous, southwest-facing slope that is deeply anchored in Kimmeridgian marl.
Wow!
The vast majority of the high-quality Premier Cru sites are also purely Kimmeridgian.
But the vines planted on the harder, younger Portlandian rock on the plateaus, where do those go?
Those form the Petit Chablis appellation.
Interesting.
Without the clay to provide the same hydrologic buffering and without the same extreme active-lime interaction, the Chardonnay vines produce a completely different biochemical profile.
So Petit Chablis is generally lighter, fruit-forward, with pretty citrus and floral aromatics, right?
Yeah. Designed for early consumption. It is delicious, but it completely lacks the profound, brooding structural tension and ageability of the Kimmeridgian wines.
So what does this all mean for you, the listener? It means when you're paying top dollar for a bottle of Chablis Grand Cru, you aren't paying for marketing.
No.
You're essentially paying for the hydrologic engineering provided by a 150-million-year-old oyster graveyard.
And that identical geological layer extends hundreds of kilometers to the west.
Wait, it goes that far?
Oh, yeah. If you follow the Kimmeridgian outcroppings to the western edge of the Paris Basin, you hit the Loire Valley. You hit Sancerre, the global benchmark for Sauvignon Blanc.
But Sancerre isn't a neat horizontal layer cake like Chablis, right? Sancerre is a geological collision zone.
It is intensely fractured, primarily due to a massive deep crustal feature known as the magnetic anomaly of the Paris Basin.
That sounds like something out of science fiction.
It does. It aligns with the Sancerre Fault. This immense tectonic shearing forced geological formations from vastly different eras to the surface, stacking them side by side.
So it's a patchwork.
You have over a dozen distinct geological periods overlapping. But for the vignerons of Sancerre, viticulture revolves around a defining triad of 3 distinct soils.
Let's break down the hydrologic mechanics of the Sancerre triad. Soil number 1, terres blanches.
Terres blanches translates to white soils. This is the Kimmeridgian marl.
So exactly the same 150-million-year-old fossil-rich calcareous clay we just saw in Chablis.
Exactly. It's called terres blanches because the high clay content turns a stark, glaring white when it bakes dry in the summer sun.
And when you plant Sauvignon Blanc in this Kimmeridgian marl, what happens mechanically?
Well, because of the massive water retention of the clay and the slow, sustained ripening it forces upon the vine, Sauvignon Blanc builds immense structural power.
So Sancerre grown on terres blanches produces broad-shouldered, full-bodied wines.
Yes, they have a powerful, aggressive acidity and a deeply concentrated herbal profile, heavy notes of fresh tarragon or crushed thyme. These are the Sancerres built to age for decades in a cellar.
Okay, so that's the clay. Soil number 2 moves us to a different rock entirely, the Kayats.
The Guydots are slightly older, dating to the Oxfordian stage of the late Jurassic, roughly 160 million years ago.
What does that rock look like?
This is a very pure, hard limestone that has been shattered by millennia of freeze-thaw cycles into a shallow layer of flat, stony gravel. There's almost zero clay in the Kayats.
So the hydrologic mechanism is completely flipped, total drainage.
Almost instant drainage. The roots sit in dry, rapidly heating gravel. This warmer, drier environment accelerates the vine's metabolic cycle.
Changing the chemistry again.
The resulting wines are entirely different from the Terroirs Blanches. Kayats wines are delicate, linear, and highly aromatic. They express vibrant, high-toned floral notes and fresh lemon zest.
Designed for immediate youthful drinking, lacking the heavy architectural weight of the marl.
Exactly.
And then we reach soil number 3, which brings us to a completely different era of deep time. Silex.
Silex skips the Jurassic entirely. We jump forward into the Eocene epoch of the Tertiary period, roughly 56 to 34 million years ago.
So much younger.
Relatively speaking, yes. Silex is a highly specific clay-siliceous matrix that is densely packed with massive nodules of pure flint.
Flint, like essentially crystalline silica. It's incredibly hard, historically used to spark fires or make cutting tools. How does a soil packed with silica impact a vine?
It operates through thermal radiation and altered nutrient uptake. Flintstones have a high thermal mass.
Meaning they hold heat.
Yeah, they absorb solar radiation during the day and radiate that heat back into the vine canopy throughout the cold Sancerre nights.
Like a space heater for the grapes.
This constant thermal regulation alters the ripening curve. Furthermore, the absence of high-active calcium carbonate means the vine processes nitrogen differently.
And this is where we get to the famous struck match or gunflint aroma of Silex Sancerre. Because it's not that the roots are absorbing the flavor of smoke from the rock, obviously.
Exactly. That's a crucial distinction. The flint rock itself has absolutely no smell.
So where does the smoke come from?
The specific temperature and nitrogen availability of the Silex soil causes the Sauvignon Blanc vine to synthesize higher concentrations of highly volatile sulfur compounds, specifically thiols.
Thiols.
When these thiols are fermented by yeast, they express aromatically as a profound, brooding, smoky, struck match character.
Wow.
The Silex wines possess an acidity that is often described as razor sharp, and they require years in the bottle to fully unfold.
So within a single appellation, utilizing a single grape variety, the decision between Terroirs Blanches, Kayats, and Silex yields a massive, powerful wine, a delicate floral wine, or a brooding, smoky wine.
Just depending on the dirt.
The geology dictates the heat and water, and the vine simply translates those inputs into chemical compounds.
The geology is the script. The biology is just the actor reading the lines.
That is perfectly stated. We have spent a significant amount of time in the Jurassic examining the mechanical impact of oysters, sea lilies, and shattered gravel.
And we jump to the Eocene to look at flint.
But there is a massive geological era sitting right between the two, which underpins perhaps the most famous wine on Earth. We have to examine the Cretaceous period.
To do that, we leave the Loire Valley and travel north, returning to the heart of the Paris Basin.
To the global epicenter of sparkling wine, we are going to Champagne.
When most people think of the geography of Champagne, they picture the Terroirs, the massive, cathedral-like underground cellars carved directly into sheer, pure white rock.
Right, those gorgeous caves.
That brilliant white rock is Cretaceous chalk. The entire foundation of Champagne is built upon immense plateaus of chalk deposited between 90 and 66 million years ago.
When the Paris Basin was once again submerged under a warm, shallow sea.
And once again, the biological factory was running.
Running at an unprecedented scale, it seems.
Oh, absolutely. Trillions upon trillions of those microscopic coccolithophores lived, synthesized their calcium carbonate plates, and drifted to the seafloor.
And over tens of millions of years, they formed a layer of almost pure calcite chalk that is, in some places, 300 meters thick.
300 meters. But Champagne chalk isn't just standard limestone. The physical architecture of this specific rock is its superpower.
How so?
It comes down to porosity and capillary action. The Cretaceous chalk in Champagne is extraordinarily porous. Between 30 and 40% of the rock's total volume is actually microscopic empty space.
Just air pockets.
Basically. However, those pores are incredibly tiny. This creates a massive capillary force.
Meaning it pulls water in.
The chalk acts as a monumental geological sponge. It can absorb and store an astonishing 400 liters of water per cubic meter of solid rock.
Let's pause on that metric. If you carve out a solid block of rock, 1 meter by 1 meter by 1 meter, it is holding 400 liters of water inside its microscopic structure.
Solid rock holding 400 liters of water. And crucially, it holds that water with an intense matric potential.
What does that mean for the plant?
The capillary pressure is so strong that the water doesn't pool or drown the vine's roots. It stays locked inside the rock matrix.
Safely stored away.
Right. During the intense heat of summer, when the topsoil is completely bone dry, the chalk slowly releases this water to the deep roots through an agonizingly slow drip feed.
But the chalk of Champagne is not a monolith, is it? Just as the Jurassic rocks varied, the Cretaceous chalk is divided into distinct layers that drastically alter how the vines behave.
Very true. Specifically, we must look at two primary biozones of chalk, deposited millions of years apart, which contain the fossils of two very different marine creatures.
Okay, let's start with the older, deeper layer, the belemnite chalk.
Formed during the Campanian stage, about 72 to 84 million years ago. It is named for the immense density of belemnite fossils found within it.
And belemnites were?
They were highly successful squid-like marine cephalopods. They had 10 arms and a soft body. But internally, they possessed a heavy, solid calcium carbonate counterweight in their tail, called a rostrum.
The rostra look exactly like heavy stone bullets or thick, pointed cigars.
Geologists frequently uncover belemnite battlefields. Massive, dense accumulations of these stone bullets, likely the result of mass die-offs following spawning events in the Cretaceous Sea.
That's a crazy visual. But for viticulture, the fossils merely identify the layer. The vital property of belemnite chalk is its physical placement and density, right?
Exactly. It is hard, highly compact, and in the most prestigious areas of Champagne, it sits aggressively close to the surface.
Okay, if you stand in a Grand Cru vineyard, how deep is the dirt before you hit the solid belemnite chalk?
Often it is a mere 30 to 50 centimeters.
Less than 2 feet of topsoil before you hit an impenetrable-looking wall of white rock. 1.5 feet of dirt is almost nothing. How does a vine even survive that?
By drastically altering its root architecture. A vine planted in shallow topsoil over belemnite chalk realizes very quickly that there is no sustained water near the surface.
It panics.
To survive, it has no choice but to force its roots downward. It must utilize organic acids and sheer hydraulic pressure to bore directly into the micro fissures of the solid chalk,
Seeking that massive 400-liter per cubic meter reservoir deep underground.
Exactly. Agronomists have excavated older vines in the Côte Blanc and found roots plunging 5, 10, even 15 meters deep into the pure chalk bedrock.
15 meters deep. So the vine is forced into a constant, highly regulated state of exertion. It's never relaxed. It's always working for its water.
And that continuous low-level stress fundamentally alters the ripening trajectory of the grapes.
Slowing it down?
The slow, metered water uptake delays the entire vegetative cycle. The grapes ripen their sugars and phenolic compounds incredibly slowly, while the cool subsurface temperatures preserve the malic acid.
Which produces the ultimate expression of champagne.
Belemnite chalk is the undisputed king of long-aging Champagne. It underpins the greatest Grand Cru villages of the Côte Blanc, Le Mesnil-sur-Roger, Cremant, Avize.
Beautiful lines.
The Chardonnay grown on this strict, deep-drilling rock yields a wine with cut-glass citrus precision, a laser-focused saline spine, and the sheer structural density required to age and evolve in a cellar for 40 or 50 years.
No, if belemnite chalk is the older, stricter layer, what sits above it?
The younger layer is the microscopic chalk, deposited during the Maastrichtian stage around 66 to 72 million years ago.
And named for a different fossil.
Named for a genus of extinct, heart-shaped, fossilized sea urchins called microscopic.
What is the physical difference between the squid chalk and the sea urchin chalk?
Well, because the microscopic chalk was deposited as the Cretaceous Sea was beginning its final slow retreat, the sedimentation was different. The microscopic chalk is physically softer and more friable.
Okay, softer rock.
But the most critical viticultural difference is the overburden, the depth of the topsoil sitting on top of the rock.
How deep are we talking?
In areas dominated by microscopic chalk, the topsoil of clay, sand, and loam can be anywhere from 60 centimeters up to over 2 meters deep.
But wait, if the sponge-like nature of the chalk is the key to greatness, doesn't a 2-meter layer of topsoil ruin the whole system? If a vine doesn't have to drill into the chalk, why would it bother?
That is precisely the hydrologic reality. Vines are inherently efficient, or to put it bluntly, lazy.
Makes sense.
If a vine has 2 meters of rich, moisture-retaining loam to explore, it will spread its roots out laterally in the topsoil. It won't waste the massive metabolic energy required to bore 10 meters into solid rock.
So the root architecture remains shallow.
Yes.
Huh.
And because the roots are shallow, they have access to easy, abundant water following rain events. They face far less hydric stress.
Meaning they grow differently?
They metabolize faster, grow larger canopies, and ripen their fruit earlier and more easily.
The resulting wines must be structurally entirely different. It's like a botanical masterclass.
How do you mean?
Well, the belemnite chalk, with its non-existent topsoil, is the strict personal trainer. It forces the vine to struggle, drill deep, and earn every drop of water, creating a tight, disciplined, long-aging wine.
That's a great analogy.
And the microscopic chalk, with its deep topsoil, is the lenient teacher. It gives the vine plenty of easy resources, requiring no struggle.
And it results in a wine with a rounder, more open, and flexier structural foundation. The wines from microscopic chalk are highly accessible, earlier drinking, with a softer, broader mineral expression.
Which has its own place in the market.
Exactly. This is exactly why microscopic chalk forms the high-volume base for almost every major champagne house's non-vintage blends. The Grand Crus on the belemnite chalk provide the prestige, vintage-dated aging potential. The Premier Crus on the microscopic provide the volume and approachability that pays the bills.
Fascinating. Now, this is all mechanically incredible. We have traced the tectonic plates, the specific fossils, and the hydrologic dynamics of clay versus chalk.
We've covered a lot of ground.
But there is a glaring mechanical gap in our story here, a biological plot hole that needs to be addressed.
What is the mechanical gap?
We have established that the rocks contain the water. We know the chalk is a sponge. We know the vine needs to get its roots down into that sponge. But rocks are solid.
They are.
Even porous 400 liter per cubic meter chalk is a rock. How does a living, fleshy plant actually penetrate solid calcite? How does a soft root tip extract water from a microscopic pore without dying in the process?
To answer that, we have to leave the macro realm of geology and enter the microscopic realm of biology and biochemistry.
Let's do it.
We have to look at the hidden engine of the vine itself. We have to go underground and examine the roots, the hormone signaling, and the microscopic battle for survival.
Let's detail the anatomy of the root system. When we look at a vineyard, we see the trunk, the leaves, the grapes. What is actually happening below the surface?
The visible canopy is really only half the plant. The root system is a massive, complex, hidden network.
How massive?
Viticultural researchers estimate that a grapevine allocates between 30 and 60% of its total photosynthetic energy, the sugars it produces from sunlight, solely to growing, maintaining, and defending its roots.
Over half of the plant's energy is spent in total darkness.
Yes. And the structural architecture of the root serves different purposes. The thick, old, woody roots act as physical anchors in the soil and act as massive carbohydrate storage tanks to survive winter dormancy.
The anchors.
But the actual biological magic, the active extraction of water and mineral ions, happens almost exclusively at the very tips of the youngest, finest, hair-like roots.
The root tips. What exactly is happening at the cellular level down there?
The very end of the root is protected by a structure called the root cap. This is a tough, specialized cluster of cells that constantly secretes a viscous, slimy mucilage.
Slime.
Yeah, this slime acts as a biological lubricant, allowing the growing root tip to physically push its way through abrasive soil grains and microfissures in the rock without having its delicate internal tissue shredded.
That's incredibly clever.
Just behind the root cap is the zone of elongation, which is covered in millions of microscopic root hairs. These hairs massively increase the cellular surface area, allowing the root to interface with the water trapped in the soil pores.
But if a root is sitting in the shallow topsoil in Champagne and a drought sets in, how does the root know to go deeper? How does the plant realize that there is a deep water table trapped in the chalk 5 meters below?
The plant operates via rapid, highly sophisticated chemical signaling.
Hormones.
Exactly. Let's trace the mechanics of a dry summer in the Côte des Blancs.
Yeah.
July arrives, and the rain stops. The shallow topsoil rapidly dries out.
Okay.
The fine roots sitting in that topsoil experience a sudden drop in surrounding moisture. The vine is entering the early stages of hydric stress.
It has to react instantly or it will desiccate.
Right. The root tissues immediately initiate the biosynthesis of a crucial stress hormone called abscisic acid, or ABA.
ABA?
The roots pump this ABA directly into the xylem, the plant's upward-flowing vascular tissue. The hormone is carried up the trunk, through the shoots and straight into the cellular tissue of the leaves.
The roots are sending an emergency broadcast to the canopy.
Yes. When the ABA arrives in the leaves, it binds to specific receptors on the guard cells.
What do guard cells do?
Guard cells control the stomata, which are the thousands of microscopic pores on the underside of the leaf that open to take in carbon dioxide for photosynthesis, but also release water vapor via transpiration.
So the ABA triggers the stomata to act.
It causes a rapid change in the turgor pressure of the guard cells, forcing the stomata to slam shut.
Locking the doors.
Exactly. This instantly halts the loss of water vapor to the atmosphere. It effectively shuts down photosynthesis and stops the vegetative growth of the vine's shoots, locking down the above-ground factory to conserve the water it still has.
That is an incredible defense mechanism, but shutting down the factory doesn't solve the problem of finding more water.
That is where the second function of ABA comes in, operating back down in the roots.
What does it do down there?
The localized ABA in the root tips acts as a chemical traffic cop. It directly interacts with the inward rectifying potassium channels in the root cells, physically blocking potassium ions from entering the upward flowing vascular stream.
Why does blocking potassium matter?
Because of osmotic pressure. By hoarding potassium inside the cells of the root tips, it lowers the osmotic potential within those specific cells.
Okay.
Water naturally flows across a semi-permeable membrane from an area of high potential to an area of low potential. By dropping the potential in the root tips, the vine literally forces whatever water it does have straight down into those growing tips.
Wow.
It hydraulically pressurizes the root cap, providing the physical turgor pressure needed to literally drive the root deeper into the microfractures of the bedrock.
So the drought above ground is physically powering the drill below ground. The plant is hydraulically forcing itself into the rock to survive.
It is a stunning mechanical adaptation, but boring into limestone and chalk introduces a completely different, potentially lethal complication. We have to discuss the chemical crisis.
The battle for iron. We talk about ancient seabeds, limestone, and chalk as the holy grail of fine wine terroir. But botanically speaking, isn't calcareous soil incredibly hostile to most plant life?
Oh, it is highly toxic.
Yeah.
And it all comes down to pH levels and solubility. Calcareous soils, because they are essentially pure calcium carbonate from marine fossils, are highly alkaline.
What's the pH?
The pH of these soils typically ranges from 7.2 up to 8.3. This creates what agronomists measure as the active lime index, or the indice de Puget.
What happens to the chemistry of the dirt at an alkaline pH of 8.0?
The chemistry of mineral solubility collapses, specifically the availability of iron.
But the iron is still there, right?
Iron is physically present in the clay and the chalk, yes. But in a highly alkaline, high-calcium environment, a devastating chemical reaction occurs. The iron precipitates out of the soil solution.
Let's define precipitation in this context. It's not rain.
Right. In chemistry, precipitation means the iron binds with the surrounding carbonates and hydroxides to form a solid, insoluble mineral complex.
It's locked away.
The iron is locked away in a chemical vault. The roots are touching the iron, but they cannot absorb it. It is biologically unavailable to the vine.
And iron is non-negotiable for survival.
It is an absolute matter of life and death. Iron is the crucial catalyst required for the synthesis of the porphyrin ring, which is the structural core of chlorophyll.
And chlorophyll is the green pigment that absorbs sunlight to drive photosynthesis.
Exactly. If the root cannot extract iron, the plant cannot synthesize chlorophyll.
And if it can't synthesize chlorophyll, the factory dies.
The leaves lose their green pigment, turning a sickly translucent yellow. Photosynthesis halts. The vine cannot produce the sugars required to grow or ripen grapes.
It starves.
The plant starves to death while surrounded by sunlight. This physiological condition is known as iron chlorosis.
And historically, iron chlorosis was an existential threat to the entire French wine industry, wasn't it?
Yes. For centuries, indigenous European vines, Vitis vinifera, had slowly adapted a mild tolerance to these soils. But in the late 19th century, the phylloxera epidemic devastated Europe.
The microscopic root louse that destroyed almost every vineyard on the continent.
The only solution was to graft the European vines onto Native American rootstocks, which had evolved a natural resistance to the louse.
But the Native American rootstocks evolved in the acidic soils of North American riverbanks and forests. They had absolutely no evolutionary defense against the highly alkaline, iron-locking ancient seabeds of Champagne or Chablis.
Exactly.
Yeah.
When they planted these American rootstocks into the chalk of Champagne or the Kimmeridgian marl of Burgundy, the vines rapidly succumbed to iron chlorosis and died.
Oh, man.
The entire foundation of terroir-driven French wine was effectively doomed by soil chemistry.
So how is the crisis solved? Science had to manually intervene.
The solution was an early, brilliant form of selective genetic engineering. In 1882, a botanist named Alexis Millarda and a viticulturist named Charles de Grasset embarked on a massive breeding program.
Looking for a superhero root.
They needed a rootstock that possessed the phylloxera resistance of an American vine, but the extreme alkaline tolerance of a European vine.
And what did they create?
They produced a hybrid that is known to this day by its unromantic nursery catalog number, Rootstock 41B.
Rootstock 41B.
It is a cross between a highly lime-tolerant European cultivar called Vitis vinifera cultivar casselis and a wild, deep-rooting, drought-resistant American species from Texas called Vitis berlandieri.
The ultimate biological lockpick.
It is an absolute marvel of agricultural science. Rootstock 41B can tolerate an active lime index of 60 and thrive in soils that are up to 40% active limestone.
How does it do it?
It survives by utilizing a highly active proton extrusion pump. The roots literally excrete organic acids, specifically malic and citric acids, along with protons directly from the root tips into the surrounding alkaline soil.
It is locally acidifying its own microenvironment.
Exactly. It lowers the pH in the immediate millimeter of soil surrounding the root tip. This localized acid drop dissolves the precipitated iron bonds in the solid matrix, freeing the iron ions.
Unlocking the vault.
The root then deploys specific transport proteins to pull the newly soluble iron across the cellular membrane.
It breaks the chemical vault, steals the iron, and feeds the European vine grafted on top of it.
And it provides a massive secondary viticultural benefit.
Sure.
Because rootstock 41B expends so much metabolic energy fighting the chemistry of the soil to extract iron, it naturally restricts the vegetative vigor of the canopy,
So it slows down the vegetative cycle.
ensuring high acid retention, smaller berries, and intense concentration in the grapes. Rootstock 41B is the invisible genetic bridge that allows great wine to be produced from toxic ancient rock.
This is a breathtaking narrative of survival, but I know the science of the rhizosphere, the root zone, has evolved rapidly in the last few years. The vine isn't actually fighting this battle entirely by itself, is it?
No, it relies on a hidden microbial alliance.
Tell us about the alliance.
The vine is merely the largest organism in the vast subterranean ecosystem. A grapevine root alone, even the formidable rootstock 41B, struggles to conquer 150 million years of geological chemistry. It requires a symbiotic army of fungi and bacteria.
Let's introduce the first division of that army, the fungi.
We must look at vesicular arbuscular mycorrhizal fungi, specifically highly adapted species like Glomus mosi.
Okay, but when we say fungi, we aren't talking about mushrooms popping up between the vines.
No, these are obligate microscopic symbionts. The spores germinate in the soil and produce microscopic threads called hyphae. These hyphae physically seek out the young root tips of the grapevine.
They hunt for the roots.
Yes. They secrete enzymes to dissolve the plant cell walls, and the fungal threads physically penetrate inside the living cortical cells of the root.
They break into the root. That sounds like an infection.
It is a highly controlled, mutually beneficial infection. Once inside the root cell, the fungus branches out to form a microscopic, tree-like structure called an arbuscule.
What does that do?
This arbuscule acts as the biological trading post. Meanwhile, outside the root, the fungal hyphae branch out massively into the surrounding soil, creating a sprawling, microscopic web.
A subterranean fungal internet.
The fungal hyphae are magnitudes thinner than even the finest vine root hair. They can penetrate microscopic rock pores that the root could never access.
Mining the rock.
The fungi mine the distant rock for highly immobile nutrients, specifically phosphorus, zinc, and iron, and pipe those minerals through their network directly back to the arbuscule inside the root cell.
And what does the vine pay them with?
In exchange, the vine pumps the sugars and lipids it created via photosynthesis directly into the fungus, allowing it to survive.
It is a subterranean bartering system. The vine trades solar power for deep rock minerals.
But the fungi are only half of the microbial equation. The heavy artillery in the battle against iron chlorosis in highly alkaline soils belongs to bacteria.
The bacteria.
We must look at fluorescent pseudomonads, particularly strains like Pseudomonas fluorescens.
Fluorescent bacteria living in the chalk.
Yes. These bacteria aggressively colonize the rhizosphere, living in the microscopic film of moisture immediately surrounding the root tip. And they possess an incredible evolutionary tool.
What do they do?
When these bacteria detect that the environment is severely deficient in soluble iron, because the high pH has locked it all away, they synthesize and deploy a specialized chemical weapon called a siderophore.
What exactly is a siderophore? Let's break down the chemistry.
The word siderophore literally translates from Greek as iron carrier.
Okay.
Chemically, they are small, high-affinity, iron-chelating compounds. Think of them as microscopic, highly targeted chemical claws. The Pseudomonas bacteria excrete millions of these siderophore claws into the highly alkaline soil matrix.
And the claws go hunting for iron.
The binding affinity of a siderophore for iron is mathematically staggering. It is so powerful that it can literally rip the iron atoms away from the precipitated calcium carbonate matrix.
Ripping it from the stone.
The siderophore forms a tight ring around the iron atom, a process called chelation making, the iron highly soluble, even at a pH of 8.0.
Wow.
The bacteria then pull the chelated iron back into their cells to survive. And because the bacteria are living in tight symbiosis with the root, a significant portion of this liberated, highly soluble iron is subsequently absorbed by the grapevine.
This completely revolutionizes how we view a vineyard. It is not just a quiet, passive plant sitting in the dirt. It is a desperately engineered survival machine.
A literal survival machine.
We have a European canopy grafted onto an American rootstock, sensing drought, communicating via ABA stress hormones, manually shutting down its canopy, pumping osmotic pressure to hydraulically fracture solid chalk.
Altering its localized pH.
Yes. Plugging into a microscopic fungal internet to mine phosphorus, and colluding with chemical claw-wielding bacteria to steal iron from a highly toxic, ancient seabed.
And that violently complex, highly orchestrated, continuous battle for survival is precisely the mechanism that concentrates the acids, synthesizes the secondary metabolites, and produces the profound structure and complexity you taste in the glass. The struggle is the terroir.
Let's synthesize this entire journey. We began with a massive 110,000 square kilometer depression in the Earth's crust, the Paris Basin.
We watched 150 million years of microscopic coccolithophore sea lilies and oysters die in warm epicontinental seas, compressing into massive beds of solid rock.
We watched the African tectonic plates smash into Eurasia, sending shock waves that shattered the bedrock, dropping the Bressy-Graben Fault to expose the dizzyingly complex hillside of the Côte d'Or.
Where a winemaker can step across an invisible fault line from wave-swept crinoidal limestone to muddy Austria acuminata marl.
We traveled to Chablis to find the Exogyra virgulacama oysters packed into the Cameroonian clay, providing the perfect hydrologic balance for Chardonnay.
We examined the Sancerrois Fault, where Terres Blanches marl creates powerful wine, Cayos gravel creates delicate wine, and Silex flint thermally manipulates the nitrogen cycle to produce a struck-match aroma.
We journeyed north to Champagne, exploring the physics of the 400-liter per cubic meter Cretaceous chalk sponge. We contrasted the deep drilling roots fighting the hard, shallow belemnite squid chalk against the relaxed, shallow roots resting in the deep topsoil of the Micraxter sea urchin chalk.
And finally, we zoomed into the microscopic tip of rootstock 41B, tracking the ABA hormones, the osmotic pressure, the proton extrusion, the glomus mossae fungal networks, and the siderophore claws of the Pseudomonas bacteria.
It is an awe-inspiring, unbroken chain of causality. Every single link, from the macrotectonics to the microbiology, must execute flawlessly to produce the wines we revere.
It really must.
Which brings us to the ultimate thesis of this deep dive. When we strip away the romance and look at the empirical science, the reality is far more magnificent than the poetry. Every sip of a great terroir-driven wine is quite literally tasting deep time.
Tasting deep time.
It is a liquid archive of the Earth's geological history, drawn up from a prehistoric seabed, filtered through a microbial internet, synthesized by a struggling plant, and poured into your glass.
It is a beautiful synthesis. But as a scientist examining this system today, I have to leave you with one final, deeply provocative thought. A warning about the extreme fragility of this deep time engine.
A warning regarding what?
The climate. This entire magnificent 150 million-year-old system relies on a very precarious assumed balance.
The water balance.
The belemnite chalk sponge, the Cameroonian clay reservoirs, the deep drilling root architectures responding to ABA hormones, they're all perfectly evolutionarily adapted to historical climate patterns and very precise, reliable deep water tables.
But things are changing.
Exactly. But as anthropogenic climate change drastically alters global precipitation, and as severe multi-year compounding droughts become the new reality across Europe, the fundamental hydrologic equation is breaking down. Soil moisture is vanishing.
And if it vanishes completely?
If the deep water tables drop too severely, even the astonishing capillary pressure of the Cretaceous chalk sponge will eventually run dry. If a vine hydraulically powers its roots 10 meters deep into the bedrock and finds nothing but desiccated dust, the entire biological engine seizes.
It raises an existential question for the future of terroir. Will a 150-million-year-old geological advantage suddenly become a fatal liability if the water table drops below the reach of the deepest roots?
Can a subterranean fungal internet or a bacterial siderophore system function in a completely desiccated rock matrix?
That is a chilling reality to consider. We revere these ancient systems because they force the vine to struggle beautifully, but that system assumes the water will ultimately be there, hidden in the rock. If the rock goes dry, the deep time engine stops running.
That's the truth of it.
That is an immense question for all of us to mull over and explore as the climate shifts. Thank you for joining us on this incredible empirical deep dive.
It was a pleasure.
The next time you open a bottle of Chablis or Sancerre or a vintage champagne, I hope you take a quiet moment before taking that first sip. Look at the liquid tension in the glass and think of the tectonic collisions, the microscopic chemical claws, and the prehistoric oceans that labored for millions of years to make it possible.
Tasting deep time indeed.
Until next time, keep diving deep.